This is M. Haritha, second year CSC B section in Adi Shankara Institution of Technology. Register number is 570S. Probability and statistics. History of probability. The modern mathematical theory of probability has its roots in attempt to analyze games of chance by Zero Magic Cameron in the 16th century and by Pyramidal Fermat and Blaise Pascal in the 17th century. Published a book on the subject in 1657 and in 19th century. Pierre Laplace completes what is today considered the classical interpretation. Internally, probability theory mainly considered discrete events and its methods were mainly congregate events analytic consideration complete the incorruption of continuous various into the theorem. This culminates in modern probability theorem on fundamentals laid by Andre Lincoln's Commerce combined the notations of sample space. Introduction by Richard van Mises and measure theory of presented this analysis system for probability theory in 1933. This becomes the mostly undisturbed automatic basics of our modern probability theory, but alternates exist such as the adoption of finity rather than countable adapt by Boran B. Filt. Discrete probability theory deals with events that occurs in countable sample space. Example, throw dice experiments with decks of cards, random walks and tossing cones. Classical definition. Integrally, the probability of an event to occur was defined as the number of cases favorably for the events over the number of total outcomes possible in an equal probable sample space. Classical definition of probability. For example, if the event is occurs on an even number when a die is rolled, the probability is given by 3 by 6 is equal to 1 by 2. Since 3 faces out of the 6 have even numbers and each face have the same probability of appearance. Modern definition. The modern definition starts with a finity or countable set called the sample space, which related to the set of possible outcomes in classical sense. Denoted by it is then acknowledged that for each number element x union trends and intervenes probability value of fx is attached with stratifies the following probability fx union 1 for all x union n. Fx is equal to 1. That is the probability function. Fx lies between 0 and 1 for every value of x in the sample space un, and the sum of fx over all values x in the sample space union is equal to an event is defined as any subset E of the sample space here. The probability of the event E is defined as P is equal to sigma x fx. So the probability of the entire sample space is 1 and the probability of the null event is 0. The functional fx mapping a point in the sample space of the probability value is called a probability mass functions abbreviated as PEMF. The modern definition does not try to answer how probability mass functions are obtained. Instead, it builds a theory that assumes that extends continuous probability distributions. Continuously probability theory deals with events that occurs in a continuous sample space. Classical definition. The classical definition breaks down when quantified with the continuous cases. See better pardon. Classical definition. The classical definition. Modern definition. If the sample space of the random variable x is the set of real number or are a subset theory, then a function called the cumulate distribution function fx defined by fx is equal to px less than x. That is, fx returns the probability that x will be less than or equal to x. The CDF necessarily satisfies the following property. F is a methodical, non-decreasing right continuous function. Limit fx is equal to 0. Limit fx is equal to 1. If f is a obtuse continuous, its derivative exists and integrative the derivative gives us the CDF backup against then the random variable x is said to have a probability density. Functional or PDF for simple density. Fx is equal to dfx is by dx for a set of E less than or the probability of the random variable x begin in E is pfx less than E is equal to sigma x ex dfx. In case the probability density function exists, this can be written as px is equal to sigma x fx dx, whereas the PDF exists only for continuous random variable. The PDF exists for all random variable that takes value in R. These concepts that can be generated for multi-decimals case of Rn and other continuous sample space measured theoretic probability theory. The reasons of the measured theoretic theorem of probability is that it defines the discrete and the continuous case and makes the different equation of which makes it used. Furthermore, it covers distributions that are neither discrete nor continuous nor mixture of the two. An example of such distributions could be mixed on discrete and continuous distribution. For example, a random variable that is 0 with probability 1 by 2 and takes a random value from a normal distribution with probability 1 by 2. It can still be studied to some extent by considering it to have a PDF of sigma x union x by 2 where sigma x is the discrete delete function. Other distributions may not even be a mix. For example, the Canton distribution has no positive probability for an single point, neither does it have a density. The modern approach to probability theory solves the problem using measure theory of the defines the probability space. Thank you.